Okay, so this tutorial is concerned with the superheterodyne receiver. So we talked about that extensively about last week. So these three questions are just going to talk about the superheterodyne receiver. Okay, so here's the first question. This is just a warm-up. All right. So consider a superheterodyne receiver that is designed to receive frequencies within 10 to 30 megahertz with an intermediate frequency. So IF means intermediate frequency. So there's an intermediate frequency of 5 megahertz. Okay. Assume that at the desired setting, the local oscillator frequency is bigger than the carrier. So this is going to be down conversion, okay, which is what we need. So first, draw a diagram of the superheterodyne, then find the range of frequencies that you need for the local oscillator to do this, and then figure out what the image frequency is, given the local oscillator. So that's totally fine. Okay. So remember, so you have your AM signal that's coming in. It doesn't have to be AM. It could be something different. It could be something, it could be any signal you want as long as it follows AM. Okay. And then what's going to happen is that you have a bandpass filter, which is called the RF stage. So this is the RF stage. Okay. So this is a bandpass filter. Let me see here. Bandpass filter tuned at FC. Okay. And then what's going to happen is that you also have a local oscillator here, right? This is tunable. So you have, it's connected to here, right? Also, it is connected to a frequency mixer here. So let's see here. So we have, let's see, so what's going on here? Frequency mixer, I guess. Oh, sorry. Okay, so let's, here as well. So, okay, so we have a frequency mixer here. So this is a local oscillator. All right, so we have a local oscillator here. All right, so we have a local oscillator omega, not omega, we'll do FLO. Okay, so you have some local oscillator which is tuned at FC here. Okay. And then we have some frequency mixer here, and then we have a, this is the IF stage. Okay, this is a bandpass filter tuned at the intermediate frequency. Okay, and then you also have a demodulator as well. A demodulator. Okay, and then you have an audio device, so some speaker, so audio device. Okay, so that's generally what it looks like. So you've got some amplitude modulation signal coming in. You have an RF stage that filters out the image frequency. We'll talk about that later. You have some frequency mixer, so this actually brings this down. So the FC gets converted into F of IF, right? And then you bandpass filter everything out. You demodulate the signal, and then you have an audio device. So that's your standard, typical superheterodyne receiver block diagram. Okay. So find the range of frequencies generated by the local oscillator because we're doing down conversion, okay? So the local oscillator, if you remember, is simply the carrier plus the intermediate frequency. Okay, so the intermediate frequency was equal to 5 megahertz. Okay, and then this ranged between 10 to 30 megahertz. Okay, so the range is going to be simply 10 plus 5 and 30 plus 5. So therefore, the range is because this is 10 plus 5 and this is 30 plus 5 because that's what's happening. So that's the range of your fundamental frequency, that's the range of your frequency. So if you're tuning into your station between 10 and 30, you have to make sure that your local oscillator is going to be your fundamental, your intermediate frequency above, so that when you actually do the mixing, you'll bring everything down to 5 megahertz. Okay, so that's B. C is if the incoming carrier frequency, so if you want to, get your station at 12 megahertz, what is the image signal, right? So what is, what is the value of the local oscillator and what is the image signal? What is the frequency of the image signal? I'll explain why. Okay, well, that's very simple. So if F of C equals 12, right, megahertz, sorry, this means the local oscillator is simply going to be 17. Okay, and the image frequency, is equal to the carrier plus twice the intermediate, if you remember. So this becomes 12 plus 2 times 5, which is 22 megahertz. Okay? So that's the image frequency. Yes, that's fine. Okay, good. Okay, and explain why. Okay, well, that's very simple. Okay? Oh, shit. Cropped out again. Hold on a minute. Okay, so this is the image frequency. Okay, so if you remember, right, if you have your, so at 2 times the image frequency, okay, so what's going to happen is that, you remember, if you're doing the frequency mixing, right, so the whole point of the, the oscillator frequency is to, bring stuff down. So remember, at f of c plus 2 FIF, right, and then what's going to happen is that if you mix with FLO, which is f of c plus f of IF, right, what's going to happen is that it's going to give you 2 frequencies, right? It's going to give you one at, so let's call this f of IM, okay? What's going to happen is that it's going to give you 2 frequencies. Remember the frequency mixing part, right? It's going to give you 2 frequencies at f of IM minus FLO and f of IM plus f of LO, okay? So what will happen is that if you do this, so if you do f of IM subtract this, what will happen is that this will give you f of c plus 2 f of IF minus f of c plus f of IF, right? So when you work this out, this will give you the f of IF as the fundamental, as the frequency. So this goes through, and that's why you have an image frequency. And this doesn't, so this one here doesn't. Okay? So that's why at twice the intermediate frequency, that will actually pass through the bandpass filter that is centered at the IF stage. So you actually have 2 frequencies that are going to be passed through the bandpass filter. So that's why you need the RF stage to attenuate the image frequency so that you only are left with the desired carrier frequency that you want. Okay? So that's pretty much it. Okay, so that's pretty simple there. So very simple. So I drew the diagram. Range of frequencies goes from 15 to 35, and then if you want the image frequency, it's just 12 plus 2 times 5, which is 22. So very simple arithmetic. All right? Okay, let's do the next question. But yeah, there's no questions here. It's pretty simple, I think. Okay. Let's see. So let's do this one. Okay, this next question. Very simple. 2. All right. So this is another version of the superheterodyne receiver. So there's an RF stage, right? There's also a local oscillator that you can use, and then there's the IF stage, and there's the demodulator. This is a more simplified diagram. So consider a single-stage superheterodyne receiver. So the range of carrier signals used for AM broadcasting will range between 540 to 1600 kilohertz. That's what's usually done. Okay. So the intermediate frequency usually in AM broadcasting is set to 455 kilohertz. Also, we assume that the local oscillator frequency is going to be bigger than your carrier. So this again is down conversion. Okay. So here are the first set of. Sorry. I knocked my cable by accident. Let me just pause this. Sorry. All right. So here is the first question, I suppose. Okay. So briefly explain the operation of the superheterodyne receiver, the functions of the RF and the IF stages. Okay, that's fine. So A, the RF stage used to attenuate image frequency. Okay, so that's what the purpose of the RF stage would be. Now okay, sorry, hold on a minute. Okay, so that's used to attenuate the image frequency. So the IF stage, okay, the purpose of the IF stage is to make sure that you get the station that you want. So the IF stage filters out all frequencies except for desired one at FC, and that's translated down to f of IF. Okay, so that's the purpose of that. And then RF stage, IF stage, and then what else do we have here? I think that's, yes? I'm sorry? Sorry, speak up, please. What? Yes, it's used to attenuate the image frequency. Sorry, hold on. My pen's died again. Let me just pause this. Okay, so this is used to attenuate the image frequency. Sorry about that. So, okay, and then this guy here, it filters out all frequencies except for the desired one at FC. So all frequencies except the desired one at f of c, translated down to f of IF. All right, so that's it there. Let's see, where am I? Okay, and that's it. Okay, and then we have the local oscillator as well. God damn. Okay, here we go. So translated to f of IF. So let me just standard. Sorry, pen. Here we go. I don't want the eraser. Give me this. Shit. Oops. Shit. Okay, hold on. Sorry. Okay, let's go here. So, sorry, hold on. There we go. Okay, translated down to f of IF. Really sorry about that. And then we have our local oscillator. So the purpose of that is to mix the incoming signal. To down convert carrier frequency to the intermediate frequency. So that's the point of that. So we have the local oscillator, the RF stage, the IF stage, and the local oscillator. Okay, that's good. So if the receiver is tuned for an AM signal with a carrier frequency FC where, it's between 540 and 1600, determine the corresponding image frequency as a function of FC and FIF. Justify your answer. Okay, that's fine. So the local oscillator is just simply the carrier plus the intermediate frequency. Okay? So that's pretty much all that is over there. So let's see, that's good. Yep. So that would be the local oscillator there, and then determine the corresponding frequency. So the corresponding frequency, right? So with this, the image frequency is simply FC plus 2 FIF. Okay? And the reason why? So look at question 1 basically. So why? Okay, that's the reason why. So this is the image. So at this, if you actually do the, if you do the mixing, that's actually what happens. So the image frequency is just twice the, the intermediate frequency. Okay, so let HR. So this is a. So what's it? So this is the RF stage. Is the bandpass filter that is defined by this transfer function. Okay, so where FO is the center frequency and alpha determines the selectivity. So alpha is actually a constant. So we have to figure out an inequality where we have to make sure that the image rejection is at least 50 decibels. So what this means is that you want to make sure that when you select the desired frequency that you want, it has to be 50 decibels above the carrier frequency. So that's actually what they're asking for. Okay, so this is part C. So the image rejection looks like this. So what's happening here is that you have to make sure that the magnitude at the carrier frequency, okay, divided by the magnitude of the image, you want to make sure that the gain over the image frequency with respect to the carrier frequency, it's equal to 50 decibels. Okay, so what you have to do here is, because this is in decibels, you have to do 20 log. So magnitude, okay, equal to 50. Okay, actually not equal, but you have to make sure that it's at least 50 or more. All right. Okay, so in this case, you have the magnitude, right? This is defined as previously, so you have 1 plus J alpha F minus F of C. Okay, so this is F of O, so they tell you to define it at the carrier frequency, which is nice. Okay, so all you have to do now is we have to take this and we need to substitute it into here and here. Okay? So when you substitute f of c in here, what's going to happen is that you're going to get 1 divided by 1 plus, and then this makes it equal to 0. So this is just equal to 1. Okay? Because f of c is over here. So fc subtract that is simply 0. Okay? The image frequency is not going to be 0, of course. All right? So what's going to happen is this becomes 1, and then 1 plus j alpha f of I m subtract f of c. All right? So that's that case here. So I need to find the magnitude of this. Okay? So the magnitude of this is very easy. It's just going to be 1 divided by, remember, so when you're trying to find the magnitude of this, the top you leave alone because it's a fraction, but the bottom is going to be square root, the real versus times the imaginary. So this is the real component. This is the imaginary component. So you're going to get 1 squared plus alpha f of I m subtract f of c all squared. Okay? So this becomes 1 plus alpha squared, and this becomes f of I m squared. All right, and let's see here. Yep, f of I m squared, and then minus 2. Actually, you know what? Let's leave that out. So the image frequency is equal to fc plus 2 fif, right? So let's substitute this in now. Okay, so if this is the case, then what's going to happen is that the fc's will cancel, and I'm just left with 2I of f, right? So what's going to happen here is that you get fc plus 2fif subtract f of c. Right, these cancel, and I'm left with this by itself. So you're just going to be left with 2, and then this becomes multiplied by 4, so you get 4 f of if squared. Okay? And this has to be greater than or equal to. Right, so that's, never mind. So this is what the magnitude would be. Okay? So now that I have this here, now I have to put in 20 log 10. Okay, so this becomes 1 divided by 1 divided by. Okay, equals 50. All right. So what I can do now, so 1 divided by 1 divided by is very simple. It just becomes, the thing by itself. So this becomes 20 log 10, and then we have square root 1 plus alpha squared for fif squared. Okay, not equals, but it's greater than or equal to. Now you have to make sure that it's greater than or equal to 50. All right, and then what I can do is this square root. You can consider this as power of half. So I can do a power rule, right? So this becomes 10 log 10, 1 plus alpha squared for fif squared greater than 50, and then I can divide by 10, take the anti-log, so then what's going to happen is that this becomes 1 alpha squared for fif squared greater than 10 to the 5. Okay, so I can divide by 10, take the anti-log, and that's what I get. So that's the condition that you need to uphold. So that's the inequality that we're looking for. Okay, so you have to make sure that the intermediate frequency and then whatever alpha you choose, you have to make sure that this inequality is satisfied. So that's what you get. All right, so that is part C. And then is there anything else? Good, I think that's it. Okay, so this will be the last question, and then I'll let you guys go. So it's been pretty easy so far. All right, so this one is a bunch of handwritten, unfortunately, but we'll deal with that. But okay, so I think we're okay here. No questions here, I think. All right, so this is the last question, and then I'll let you guys go. Okay, so part of a frequency division multiplex signal is shown. This frequency division multiplex signal consists of a double sideband suppressed carrier signals of transmission bandwidth 10 kilohertz each. Okay, and the frequency division multiplex signals received by a single stage heterodyne receiver. So this is what the spectrum looks like, and then this is the superheterodyne receiver block diagram. This is pretty much the same as we did before. You can use any demodulator you want, right? So this is a coherent detector, or you can use an envelope detector, whatever you want. So that's what the block diagram looks like. And then this is the first question. Okay. If the intermediate frequency is 410, all right, and we see that the local oscillator frequency is bigger than FC, so we're doing down conversion, Determine the local oscillator frequency FLO such that the receiver is tuned when we want to take a look at the station at 740 kilohertz, and then repeat that again for 750. Okay, well that's very easy. So for part 1, the local oscillator is simply the carrier plus the intermediate frequency. So this is 740 plus 410, which is equal to 1150 kilohertz or 1.15 megahertz. Okay, if you do the same thing for 750, simply the same thing. So 750 plus 410, it's equal to 1160 kilohertz. Okay, that's pretty simple. Okay, also determine the image frequencies. Okay, that's very nice. So the image frequencies are just going to be the carrier plus twice the intermediate. Okay, so this becomes 740 plus 820, so 2 times 410. Okay, which is 820. Right, and let me just double check to see what that is. It should be 1560, right? So we get 1560 as the input. Of course. So okay, sorry. Okay, so this is 1560 kilohertz. Okay, if you want to figure out what the image frequency is for part B, which is at 750. Okay, it's just 1570. Okay. So those are your 2 image frequencies. Okay, so 820, yep. Okay, so that's B, that's fine, that's part A. Let's do part B, which is this guy over here. Okay. Determine the frequency of the oscillator in the coherent detector to demodulate the output. Okay, well that's very simple. Remember, the intermediate stage is fixed. Okay, remember what you're doing is you have an intermediate stage where the bandpass filter is going to be centered at the particular intermediate frequency stage. So because it's fixed, all right, all you have to do is you just have to make sure that the intermediate frequency is simply equal to 455 kilohertz. Okay, because that's the point of the intermediate stage. It's because what you're doing is you are using the mixer to bring all your frequencies down to where the intermediate frequency is, which is where it's centered at, and then you have to make sure that, let me see, so determine the frequency in the, yeah. So if you take a look at the diagram here, this point here, what this does is that it down converts to FIF, okay? So this is modulated F, so all you need to do here is you have to make sure that this is equal to F of IF because it's a coherent detector, so it's a coherent demodulator. So when you multiply by F of IF, when you have your cosine, you're gonna do your double sideband suppressed carrier modulation, so you're going to bring your signal down back to the baseband. So remember, this down converts to FIF, so you need a converter that will multiply your signal by this much so that you can actually down convert back to the baseband. Okay, so FIF is 4.5. Because remember, the IF stage is fixed. Okay, therefore the components get shifted down by FIF, and this is the new carrier frequency, and then that's how. So you just leave it fixed. Okay, and this is the last question. I'll let you guys go. Really sorry that it took this long. I should have been done like an hour ago, but that's unfortunately the way it. Oh, sorry. So let's undo move. Okay, let's. Put in the last one, which is this guy here. Okay, this is the last question, and I'll let you guys go. Okay, so the double sideband suppressed carrier signals in this example have a transmission bandwidth of 10 kilohertz. All right, so what's going to happen is that we have 2 filters. So let the filter at the receiver in the RF stage be this, and then let the filter at the intermediate frequency stage be this. Okay, so let the frequency responses, be of the above. And then if the receiver is tuned to receive the signal where the carrier frequency is 740 kilohertz, figure out what the attenuation is between the RF and the IF stages. So what the attenuation here in this case is how much of a gain is applied to each of the signals in the stages. Okay? All right. So let's see what's going on here. So before we even continue, let's actually draw these out. So what's happening here is that you're drawing a rect function where so this here is actually our carrier frequency. So this is tuned to be our carrier frequency. So what this is telling us here is that whatever frequency you're tuning into, you have to make sure that that is your carrier frequency here. And then here, this would be 455 kilohertz. So this is actually defined in omega, but we're going to do it in terms of F to make things easier. Okay? All right. So let's see here. So let me see here. So it's tuned at 740. So what's going to happen is that the input that's coming in is going to look like this. So 1 and then 2. So this is 740K kilohertz. So this is the input that's coming in. So this is your frequency division multiplex signal. All right? And then what's going to happen is that this is what the filter for the receiver stage looks like. So how this works is that between plus minus 20,000, it's going to reach 0.7, then everything else is going to be 0.3. So 0.7 plus 3 is 1. So what's going to happen is that it's going to look like this, 1. So this is between 740K, and this is 720K, and this is 760K. So it's going to look like this. You have 1 and then 0.3. So it's going to look something like this. Oops. Yeah. So, okay. So that's what that filter response looks like, because between 720 and 760, 0.3 plus 0.7 is equal to 0.1. And then the intermediate stage is going to look like this. So what they're asking you here is that it's okay, so 0.9, so 455 plus minus 10. So it's going to look like this. So this is 0.1. This is 1. So this is 455. Was it 455? Yeah, 455. And this is 445K. K, and this is 465K. So it's going to look like this. All right, so that's what the filter responses look like. Okay, so we have to figure out what the attenuations are for the image component. So let me see here. So receive this carrier frequency, determine the attenuation of the corresponding image component. Okay, so that's what. Okay, so what's happening here is that, all right. So remember what the image frequency. If you remember what the image frequency was at 740, it was equal to 1560, right? So 1560. This is image frequency. 1560. Okay, so 1560 kilohertz, I think, right? Let me see. Yes, it was signal. Okay, that's fine. Okay, so what's happening here is that at the RF stage, so you have your frequency division multiplex signal. 1560 is going to be right over here somewhere, right? So 1560. So what's going to happen is the signal here gets attenuated by 0.3. So 0.3 is here, okay? And then what's going to happen is that when you pass it through the intermediate frequency state, what's going to happen is that this image frequency, the image frequency is going to map to here. So FIM will appear here as well. Okay, so what's going to happen first is that your signal gets attenuated by 0.3, right? And then when you go through the superheterodyne, when you mix it up, what's going to happen is that this 1560 will appear here right at 455, and the attenuation is equal to 1. So therefore, the attenuation is 0.3 times 1. Okay, so this is because of the RF stage, and this is because of the IF stage. Okay, if you actually want to do a little bit of a bonus, the signal actually doesn't get attenuated at all, the actual signal itself. So the attenuation is for the image. Okay, for the signal, it is just 1 times 1. Okay, because the RF stage, because this is from the RF stage, and this is from the IF stage. Because at the RF stage, you're not doing any attenuation, because this is the desired frequency. Right here is FFC, right? So at 740, right, the gain is 1, and then when you shift it down using the superheterodyne, it's going to go to 455. It's also going to be 1. So the total attenuation is the RF times the IF, and then that's what you get. So this is equal to 0.3, and this is equal to 1. So 0.3 as the attenuation for the IF stage, RF and IF for the image, and then for the signal is just equal to 1. And I think that's all I have here. Yep, that's it. So those are my 3 questions. Okay, so very, very simple. All right? Okay, I wanted to end an hour early, but my pen kept on screwing up. So we have finished FM. Okay, so next week we're going to start a brief probability and random processes review, and then we'll actually get into the last part of the course, which is noise analysis and communication systems. So optimistically, I'm going to finish the whole course by next Friday. And then we're going to have a week's worth of review, and then your final exam is going to be the week after. Okay? So I sent you an email last week telling you when the final exam day is. I don't know what exactly will be on the final exam. I have to figure that out. But I just wanted to send that information to you because I know some people are traveling or some people have arrangements that they're making. So the final exam is Monday, July 4th, 9 to 12 in the lower ground. I believe it's E&G LG 10 or something. I have to take a look, but it's going to be on Monday, July 4th. Okay? So thanks for coming, and I'll see you next week.